Yeah, can you see my presentation? Just short, and can you hear me? That would be important. So, is it readable and can you hear me? Just some feedback, both. Fantastic. Thank you very much. Okay. So, hello. Thanks for coming to the emBO and to this presentation. My name is Nino Vidovic. I'm a software engineer at SEGGER, and this year I'm going to talk about how or the journey that we had last year when trying to implement a modern C++ standard library into our existing toolchain and IDE. Last year, I teased this a little bit in my talk about our C runtime library. You can look at it. I think it's on YouTube on the Nerd Force channel. Talk was called Every Byte Counts. So if you're interested in this as well, there's some more insights there. But today it's a C++ standard library, so let's dive right into it. So where do we start from? So as said, we have a toolchain and IDE that's called Embedded Studio. And so far, our focus was mostly the bare metal C world, essentially. So our C++ support was there, but it was maybe not at the level where it should be for modern C++. And so far, the library that we provided with Embedded Studio was the STL port. For everyone who's familiar with the STL port, it's simply a legacy library. It has fully support for C++ 98, and it was last updated 2008. We, of course, had customers that said, okay, we want some more modern features, especially for C++ 11, which is used on embedded targets. So we did the expansion of the library ourselves in some points. So some C++ 11 features were there, but, well, we saw a demand for something better. As more and more people from the C++ world are coming in. And this is something that we wanted to change and improve. So we set out to this task last year, and we're looking at the different standard libraries that are available. So there are, of course, a lot of different competing ones, as you probably know. In the end, we picked the libc++ from the LLVM project. The most important reason was that they're already focused a lot on small and fast code, which in our usually size and speed constrained systems that we are on embedded is something that we're looking for, and it fits nicely with the rest of our toolchain, which is also designed with this in mind. And if you're wondering why there's a dragon on my slide, it's actually the logo from the LLVM project. I was surprised myself and I liked it, so it's on my slides. But yeah, so we have picked actively maintained C++ library, and that's and we have our embedded studio system with the IDE, which is established and works fine. So we just put 1 and 2 together, press compile, and everything works, right? But not exactly. So yeah, this is essentially where the journey starts. And these are the key points of the library here. So we have the libc++ library, which is actually 3 libraries that make up the libc++ library. We have libunwind, libcxxrb, and the libcxx library. So what are these individual libraries? We look at libunwind. It's essentially your generic backtracing library, for stack unwinding. And little bit of history here. So it was for which is the library that is used in the libc C++ project was implemented by HP originally and was ported by Apple to be used with their plain ++ compiler and toolchain to bring the lib unwinder to platforms that did not have such system. And this was also intended to be small and fast. So again, it fits nicely into this narrative that we have certain constraints on embedded targets that we have to keep in mind. The next library is the libc66abi library. So abi is application binary interface, and essentially a low-level interface between two software modules like your user code and the library. And you can think of it in simple terms, like what an API would be on high level. The ABI is in simplified terms something on low level. And the one used here in the libc C++ project is based on the Itanium C++ ABI. So looking at all these words, what pops out for me was, when I researched this topic, was the word Itanium. I was wondering, okay, all other words we see are more of a technical nature and you kind of know what they're about, but I was not sure about Itanium when I first read it. Is it the new material of Captain America's shield, or what's going on with that? So I dug deeper into this topic. So a little sidetrack here, maybe for everyone who is interested. So it's actually Intel Itanium. So Intel released an architecture around 2000, 2001, and it should be it was high performance 64-bit architecture, and essentially they wanted to end the RISC era. Look, this is all the marketing stuff that they shouted back then, and they were like, yeah, this is the future of computing and nothing will beat it. And essentially what they did is they created this ABI for this architecture, but it was luckily not platform specific. That's why it was picked up by this project, because it could be ported relatively easily to other architectures. To finish the story, the architecture actually flopped, so marketing was a bit maybe ahead of its time, and it was discontinued in 2019, which kind of surprised apparently their customer base, because this launched a lot of lawsuits between big companies like Oracle and HPE, because essentially they were telling each other that their support contracts are no longer valid, and a lot of lawyers got angry and they sued each other. So if you want to look it up at Google, it's a very interesting read. But yeah, essentially I found it a little bit ironic that essentially we are using a library here which was based, which was intended to destroy RISC architectures, and in the end, we're now using it to bring actually modern C++ to RISC. So yeah, found it interesting. If you didn't know, now you know. The last library in this package is the libc66. So it's your C++ standard library. Again, the promise is fast and small code, so we like that. And current development status is that C++14 is fully implemented and supported. So you have your container templates and algorithms and all this fun stuff that's listed here, and many more. And C++17 and 20 are essentially work in progress right now, where I think 17 is mostly implemented and C++20 is on a good way. So that's what I meant with, okay, we try to pick an actively or relatively actively developed library as basis, especially compared to what the SPTL port was. So that's why the lib C++ was picked. So yeah, let's start configuring and testing. So okay, we got this library, we got these three parts of the library. And we now have to find out what needs to be ported, what needs to be changed so it works on the architectures that our toolchain supports. What we support right now is ARM and RISC-V. So we looked, okay, we have these libraries which already maybe exist, which do we have to supply, what is necessary to bring this to life. So first we looked at the libanwide library that I mentioned first, and it was initially not available for RISC-V, so we had to implement it ourselves. And then after doing this, we found the ARM variant was luckily already there, so we could skip the work there. That was very good because the RISC implementation was RISC-V implementation was not trivial, but it was doable. And what we also had to update, which we did not expect first, was our linker, or SEGGER linker, because the exception handling schemes are actually architecture specific. So I believe it was that for ARM it was implemented for RISC-V. It again was not implemented yet, so we had to do this as well. Additional configuration. So it was not the end of it. To remember, our target is bare metal embedded applications. So there's still configuration that needs to be done that the library requires. One part is atomics. Another we found was multi-thread support, and file handling, so streams are supported. This is actually, in this case, for this library, I'll talk about more about it in detail later. It's pretty much dependent also on the C library. And we'll get to that in a couple of slides. So yeah, we looked at these points and looked, okay, what are they and what needs to be done to make them work. And so we looked at atomic operations, and actually we decided that for us, for the target platforms that we're looking for, and it does not make sense to limit or implement them in a way that would only work on certain OSs or systems that the software would run on, because it's specific to the OS or system that you're going to use. Also, it has a very limited use on single core devices, which are still, for the tiniest embedded systems, it's still they still have the biggest market share. And yes, there are more and more multi-core devices becoming available, even small form factors with low power and everything, but single core devices still dominate. And yeah, atomic operations are not very useful there, and especially as there are other options to achieve this functionality or to mitigate the issues that you get if you're not using atomic operations, for example, interrupt blocking. And this, for similar reasons, we also decided thread support would be disabled in the library. So we leave it up to the user to decide if they need it or not, so they can supply their own system-specific implementation, because we don't want to constrain anybody here in some idea that we have that will not work for most of our users. So configuration. Again, I might repeating myself, but this is simply what we're aiming for, is the smallest microcontrollers, right? That C++ must work even there, not only on our big embedded Linux machines that we're familiar with, but we need to go to the couple of kilobyte devices as well. And yeah, the big elephant in the room, you all know, are exceptions, and depending on the usage, they create large code overhead. Luckily, most toolchains have an easy fix for that, where you just have a compiler flag, you turn it off, exceptions are off, you can use all that memory for other stuff. Great, right? But this also means that your libraries have to follow. So this is also something that we have to keep in mind when porting this library, that we have two library variants essentially, where exceptions are enabled and one where exceptions are disabled. So if your system has the memory, the resources, use exceptions. If you don't have it, you can turn it off, and this way both user groups are happy. Another important thing that we left in for all library types is the runtime type information, simply because it's already widely used in most embedded C++ applications. And what we found also interesting was that they actually allow something like exception compatible behavior. It is more technically and detailed explained in the papers here I'm referencing. So the zero overhead, deterministic exception throwing values from Herbstata from Microsoft, and the low-cost deterministic C++ exception for embedded system from J. Renwick et al. And from the University of Edinburgh. I hope said Edinburgh right, so none of our Scottish friends are offended. Yeah, if you need links to these papers, I can provide them on demand, but you can simply Google for these terms and they should pop up. So they explain here essentially how you can use like this runtime type information and other information that you have in your C code to get something that allows you to get the exception features essentially. So yeah, as mentioned, in this case, the modern C runtime library was needed. This is the prerequisite for the libc++. There might be other C++ libraries that are like an all-in-one package that provide all needed functionality themselves, so they can work standalone. This was not the case for the libc++. So we had to look for the runtime library. Luckily, we already had one called mrun, which is our C runtime library that we also developed with the purpose to run on this small and embedded targets. So yeah, this was our obvious pick because it was already done. So why should we reinvent the wheel, right? And yeah, in my last year's talk, you can see some use cases and benchmark performance about it. And luckily, most of the features were already available that the libc++ required. But the prerequisite was full C11 support, so C, not C++, C11 support. So yeah, we had to upgrade that as well. Why did we not have this upgraded yet to full C11 support was that again, we saw that it was not specifically necessary for the systems we're targeting, because again, we're here on bare metal embedded target systems, and one prerequisite was file support. So for your your fopens and stuff like that. And our approach was to say, okay, on a bare metal embedded target device, you don't necessarily need a file system to have a LED blinking, right? Also, the development approach in the embedded world that we know of is usually you would get some embedded software, either a library or you write your own file system, essentially. So for example, we also have a file system in our offering called mFile. Yeah, we're very consistent with the naming there. And there, the approach would be that you essentially use the file system function or the file system API that your file system software provides, and not necessarily standard library, but you could still hook into the standard library. So if you had your fopen call, you would wrap the low-level function below that with the or inject the your middleware library, like mFile, for example. So you would have your file system still be the standard library without the standard library actually providing it, because again, we can't predict what file system will your system use. But the libc++, especially the tests and the feature compatibility required file support. So we solved this with semi-hosting. So it works on all platforms and we can use the libc++. To get back to the topic, why exactly did you pick mRun? Well, I said it was the obvious choice because it's there. But there's also, of course, smaller and faster, and you can read the benchmarks on our blog, or you can also, I think on our website we have some benchmarks where we compare the library against other proprietary competitors and some the open source libraries, and the numbers are quite in our favor. But another point that we added recently and which we think is a very great thing for C++ as well is that this C runtime library actually guarantees you fast. Well, okay, fast is always relative, but in this case we are very fast. But what's more important is the constant time heap operations. So what our promise here is, or our guarantee even, is that any of your heap operations will, in each worst case that can happen in a certain time frame. So we set essentially a maximum of instructions per architecture that any heap operation will take time in. So you can always on embedded systems, it can often happen that you have time constraints that you have to hit. And you all know that the longer your application runs, heap gets fragmented, the list gets longer, so each heap operation takes longer and longer in the standard implementations. But here we focus really to optimize this worst case scenario and say, okay, we have to cut this down, and no matter what happens, no matter how badly your heap is fractured, we can guarantee you a constant time, so you can always predict how your system will behave, no matter how long it runs. There's also an interesting story how we came to this on our blog. I think it's the latest blog post, but don't quote me on that, where essentially my colleague that's in the toolchain team, Paul Curtis, like he always has his say fun projects over the winter holidays, where he programmed a little what was it, a chess simulator essentially, where he tried to how to have like a trainer which predicts you which move is the next move would be the best one, so you can learn chess better or something like that. And what he found that when he wrote this in C++ is that at some point the heap, well, it's called heap corruption, got so bad that the worst case runtime was longer than the match time that he had, like when he was playing speed chess, where you have 10 seconds to find the next move. The heap operation took longer than this 10 seconds, for example. And that was a problem that he tried to fix, and this is how our constant time heap guarantee came from. So we can always hit that timing target, no matter what happens. So if you're interested, check out the blog. It's a pretty interesting read. So yeah, finish line. So we did a bunch of configurations. So we ported, the libunwind library for RISC-V. We updated the SEGGER linker. We updated the C runtime library. We tested so many different compiler configurations, library configurations. Had to play around with the exception support, see what can we do with atomics and thread support, testing, trial and error. So weeks of work, but yeah, in the end, it worked out. we got a result. We now have a library that we can use with our toolchain, and it got upgraded from C++ 98 to C++ 14. So I guess that's a success. Again, there's also some C++ 17 and 20 features that the library comes with, of course. And the total time spent was approximately 6 work weeks over 4 months. And yeah, was this whole thing worth it? Like, it's a lot of work, right? And yeah, we think so. So it's we call it mRun++. So again, we're very consistent with our naming. And disclaimer, we're in no way affiliated with emBO. We came first. So just making sure there's no confusion there. But yeah, it's now available in our IDE Embedded Studio. Easy to use, so it's really just like when you install Embedded Studio, for the most popular architecture for ARM and RISC-V, the libraries are pre-installed simply, so you just have to enable them in your project and you're using them. That's it. You don't have to think about anything. How did we make this happen, or will the stuff work? It will simply work. And it is also possible, of course, to run the or to get the library to run in external toolchains. You can also you if you like I talked to some of you already, and not everybody's fond of GUIs, right? But you can of course call all these tools via your make scripts and stuff like that. So there's no limitation there. And the sources are also available because for the customers, for example, for other toolchain vendors, because we saw that for especially in the RISC-V market, there's a big demand for this, as the how chip architectures are created now has a bit shifted. Before you had someone like Microchip or ARM who give you the architecture, you get their tool chain, and they're only sub variants of the same architecture. But with RISC-V now you have so many different silicon vendors that supply their own architecture essentially with their own RISC-V extensions. And this is something where such chips silicon vendor or IP vendor would typically also provide a tool chain, so all these features that they thought of will actually work. And the idea here is also that they can also decide what the target platform, what the OS that runs there will be. So the things I talked earlier with, okay, for us, it does not make sense to constrain anybody with atomics and threads that would work only on a subset of OSs or RTOSs. Such a silicon vendor can say, okay, we target only this version of embedded Linux or whatever, or this RTOS, or we have this specific SDK or system that we want to run with. So they can define atomics, they can have multi-thread support and all this fun stuff. So yeah, that's why it's important to have these sources for integration for such other toolchain vendors. And yeah, that is it. That is mRun++. Thank you for your attention. If you have any questions, I do not have the chat open. If there are questions, I'll try to read them now. There are a couple, I believe. Let's see. I'll start at the top. I'll check. I did not get any. Okay, everything is in the room chat, so I hope I'll find the top. Both. There we go. Listening. Okay, Fran. Comment. Unit testing. Oh, okay, that's us. There. I think Sven A had the first question, if I'm not wrong. If you disable exceptions, how are you dealing with the use of STL? What happens if a container throws an out-of-memory exceptions and exceptions are disabled? Well, if you can, of course, I'm currently not sure how if it would build, to be honest. If you disable it in your compiler and in the library, or if it will be just filled with a dummy. I will have to check. I'll ask the team. I think Johannes is in the audience. He's from the toolchain team. So if you come later to us, we can talk about it, because I'm currently not sure what actually would be the behavior there. Found the current solution lacking. Yeah. The thing is, what we found is, we come from this very very size constrained and small embedded world perspective, essentially. And what we found lacking is that while this is freestanding solutions were providing a good, like, we're not trying to bash anyone here. Look, all the projects all have their reasoning and the reason to be there, and will fill certain aspects of user bases or use cases that are necessary to exist. But what we found is that for the really small and size constrained systems, it was tough to get them fit essentially into the target systems without having a complete toolchain behind it. So with our linker, with our own compiler, with our own C runtime library, that are all targeting exactly this one system. So it's simply faster, it's simply smaller than anything that's available out there. And with the C++ library that we add on top on that, we now can bring modern C++ to such platforms without much hassle. So this is also one thing. Our motto is it simply works. So I know you guys are all pros, right? You guys don't need the GUI. You guys have your make tools. You work from command line. You have your but that's not essentially what the majority of engineers on this embedded engineers on this planet do. And we also have to make sure that they can work with such tools in a simple matter without having to break their head around, oh Jesus, well, how does a library, how does the toolchain essentially work? So yeah, this is idea here with most of our products as well. And now we are interested in how also the feedback will be. So feel free to try and build a studio out. You can, for private and educational users and evaluation, you can use it freely. There's no licenses or cost required. Just download it and you can use it with all functions and functionality. And we're really interested to feedback, like what works for you, what doesn't work for you. Ideally, the feedback is constructive so we can improve stuff. And yeah, we're really looking forward for as much input from the C++ world as possible. So yeah, you can have the tools that you need, right? Oh yeah, the Johannes provided an answer to the disabled exceptions question. So the answer for the people in the stream: when you disable exceptions and use the non-throwing library, new cannot throw but returns null. This does indeed cause issues in the calling code. So that question being answered now as well. Okay, I think there are no more questions. I will clear the stage. If you want to talk about it, I will be around until the end of the emBO, definitely. Otherwise, just visit our website. You can just under support, you can open a technical support ticket if you have questions or stuff like that, and our engineering team will try to find a solution with you. Thank you. Goodbye.